Continuing off from last video, we left off at finding secant and tangent line slopes. So in this video, I just want to apply that concept a little further with some actual work problems. So here we have a car that is driving along a straight road, and we have its position versus time graph. So as you can see here, as the time increases, what we notice is maybe from 0 to 1, it really only traveled about like 15 meters. But from 1 to 2, it actually traveled to about 30 meters. So in a sense, this isn't a linear increase, right? Like this isn't a linear line. So we can't say that it's increasing the same amount of distance per second. But what we do have is a curve almost. So we are driving more distance per second, you could say. And that's the point of this problem. So the first task of this problem is to find this car's speed between t equals 2 and t equals 4. And so what does that look like? Well, when it asks us to find a speed, that's also known as the average rate of change. Average rate of change, right? Which we can call my secant line. Now let's draw my secant line to visualize what's going on. So if I look at t equals 2, there's t equals 2, and then here's like t equals 4. If I draw a line between these 2 points, I get like an average rate of change. This is like telling me by how many meters did we change per second if we find the slope of this line. So this once again is my secant line because it connects 2 points. The keyword is 2 points. That's a secant line, right? So let's go and try finding that average rate of change. So I'm going to plug in t equals 4 and t equals 2 into my function. So we're going to say plug in 4 and 2 over 4 minus 2. So this continues the formula that we were working with last class. And then we just had to start solving. So I'm just going to bring this down a little bit and solve where we have a little bit more room. So here, S of t, just so that we have it up front, is 5t squared plus 3. So we could do two things. A, we can plug in numbers, or B, we can look at the graph and make some approximations. I'd rather just go ahead and plug in numbers, right? So for S of 4, let me write it like this. S of 4 equals 5 times 4 squared plus 3. That gives me 83. And then S of 2, 5 2 squared plus 3 gives me 23. And now we can plug this in. So we have 83 subtracted by 20 over a change of 2 seconds. And this gives me 30 meters a second. Right? So that's the average speed of the car. Right? This isn't what your speedometer shows. But now if we start talking about instantaneous rate of change, there's something different. We're talking about an instantaneous rate of change at t equals 2. So looking at my graph again, at t equals 2. And if I were to draw an approximate tangent line, I can't say for sure, but that looks about right for what my tangent line will look like. So we need to find the slope of that. But realize we really can't find the slope of 1 point only, right? We need 2 points. For that reason, we're going to take a point right next to it. Okay, what we're going to do, we're going to take a point right next to it. So the instantaneous rate of change which is associated with a tangent line, what we can do is just take a point right next to it. So I'm going to say that I want to be different by some h. And we talked about h last time. It's just a small distance between 2 points. right? So now we can do 2 plus h minus 2, which just simplifies 2 over h, right? To keep it simple. And now we can solve. So the first thing I want to do is make h be small. Make h small. And a good number for that is when h will equal 0.001. All right, that's a very common number that's used in like the data science world as well. So then I can say that S 2.001, right, adding that h along, minus the position at 2 over, which just leaves you with h. And now we can start plugging in. So I know that S of 2.001 is going to equal, if I plug it all in, I get 23.02001. And then just S of 2, as we found earlier, was just 23. So now we can plug it in. 23.02001 minus 23 over 0.001, which will get me, let me bring a little bit up. This is going to give me 20.01 meters per second. And this is what you see in your car dashboard whenever, if you're driving on the road, this was you. This is the instantaneous rate of change. This is what your car is showing. Remember, it's taking a point now and immediately right after, and then telling you that amount on your dashboard. All right. So that's what your speedometer shows. And then finally, I have like a visual for you all to see. Right. And I exactly show this in the visual. And I want you to realize how, so the colors are mixed up, sorry, but the purple is my tangent line. This is my tangent. Right. And the orange is my secant, all right? So, because it's connecting 2 points. But what you can see here is that if I follow this orange line, just follow it, right? Realize how at its point of t equals 2, it doesn't do a good job of representing what the slope is at that point. Yes, it does encompass the slope between t equals 2 and t equals 4, but it doesn't really do a good job of encompassing what's happening at t equals 2. That's why your tangent line does a way better job of that. So realize now, this is the tangent line, how it's doing a way better job of representing the slope at that point, right? It's touching it at once and it's representing about how the function is at that point, right? So that's all I really had for this video. See you in the next one.